Yeah, so the question was about dimensional stability. So from the word itself, you can understand essentially what you're talking about. There's certain dimensions associated with every structure. It could be part of a component, it could be the whole aircraft, let's say the wingspan or the chord and the chord distribution along the span, etc. The aerodynamicist has designed it and optimized it for a certain mission. So you would want, as a team, these dimensions to be maintained within a certain range. You don't want it to exceed a certain range because of certain loads coming on the wing or come below a certain level. So that is essentially what we're talking about as dimensional stability when we're saying that, yes, because of the loads, there will be stress and therefore strain, which means there will be deformation, and therefore there will be a change in the size and shape of each structural component, and therefore the overall wing. But is it within the allowable limits? So that's essentially what we are talking about as dimensional stability over there.
So, but I mean, the question came in for looking at these payload adapters, which mount these sensitive instruments, and they are using aluminum magnesium alloys.
Okay, okay.
One of the terms that that it is specific.
Yeah, yeah. So essentially what they're talking about from a material perspective is, so this is the requirement from the structures perspective or the overall flight vehicle perspective. So when you're choosing the material, there are certain components where the dimensional stability is of much more significance compared to some other components. So for those components, you will choose those materials which are not going to have very large deformations, which means for a given particular load or stress level, it is having as less deformation as possible, which in turn means that the strain, the maximum strain that it goes through is less. So whereas in the case of most metals, what you would have is, because they're ductile, beyond the yield also they will go, and so the actual failure limit for the strain will be fairly large. Whereas in the case of a lot of composites, because of the brittle failure, it will be large stress at which it is failing, which is the strength of the material, but the strain at which it fails will be fairly small. So in other words, even up to the very failure, actual failure, the amount of change in the deformations or the overall shape and size of the structure will not be that much. So that's essentially what we are trying to refer to. So from purely from a materials perspective, we are talking about the maximum strains it can go through, or rather than maximum strains, more at the design allowable stress. So what is the design allowable stress for that particular component? What is the design limit load, or based on that, what is the stress? At that stress, what is the strain value? So if you compare two materials and one is having a less strain for the same stress, then it is having better dimensional stability, and therefore you tend to choose that material over the other material. Yes. So essentially, that's one way of looking at it, especially because we are within the linear regime. So that's another way of looking at it. Yes.
Because I mean, in general, they're using a different alloy, the 2 series aluminum alloy, the aluminum copper, which has better yield strength and ultimate strength. But when it comes to these components, they are specifically using aluminum magnesium alloy.
Okay. Okay.
Which has a lower property actually when we look at the.
Yeah, that might be strength-wise, but as you mentioned, you must check on the Young's modulus-wise. Is there a difference? If it is having the aluminum magnesium alloy in question is having a larger Young's modulus, even if it is having probably lesser strength, as you say, it might still be a better one in terms of dimensional stability. Between composites, for example, sometimes over carbon fiber composites, which is considered to be kind of the standard as far as aerospace is concerned, both in terms of two different categories. One is pan and there's another pitch-based carbon fibers. So based on that, in one case you have larger stiffnesses, the other case you have larger strengths. But when it comes to dimensional stability, sometimes boron fiber composites are preferred. Boron fiber is actually a carbon fiber with a boron coating over it. So that makes it a little larger in diameter, each fiber. But overall, in terms of the Young's modulus, it's much higher compared to even the highest pure carbon fiber kind of a composite. So that's the reason why, for example, certain, I think I was giving this example earlier also, maybe for certain space antennas which are very long, you might prefer that boron fiber composite, because even a small change in the deflection can affect the orientation and or the performance or which location the satellite is focusing on through that antenna. Yeah, any other questions based on the last time? So I think your first assignment is due by midnight today. So please submit it on the Teams platform if you're familiar with that. If some of you are not familiar, then you could probably get in touch with either Rajesh or any of your other classmates who are familiar with it. Also, Fanindra is also there, one of the other teaching assistants with us. So in the previous class, we talked about, apart from the fundamentals, 5 different Fs which make this course more state of the art. So we will not go into the details of those, but we will try to give a flavor for it and blend it along with the fundamentals, as I said. And after listing out the 5, we started looking at how we will handle each one of these 5, and I think we covered these 3. One is the FRPs, the other is failure along with flutter and such other instabilities, and the third was the fracture mechanics. So for each one of them, I mentioned certain ways in which we would be tackling it. These are not the current state of the art. There are many better ways or more advanced ways of doing it, but this will be good enough for a generic overview for most flight vehicle or engineers who are associated with either design and or analysis of that, whether or not they are dealing with structures in particular. So apart from these 3, there are 2 other Fs that we introduced. Now we will start looking at how we will probably address them as well. So the 4th one we talked about is the fatigue, and in fatigue, essentially what we are trying to look at is there's a cyclic loading which typically happens. So you have for any given material what is known as an SN curve. So where N is the number of cycles of a particular loading and S is the strength, and this strength typically comes down, and depending on the material there could be certain different ways in which this behaves. So this is essentially your static strength, and the strength will slowly start coming down, and typically this is plotted on a log scale as well as far as the number of cycles is concerned, because it could be running into, let's say, depending on the particular structure, many tens of thousands or even millions. So essentially what you're looking at is this drop in strength which is happening, and or for any given level, you can think of it in another way. If this is the level of the maximum stress that is being applied, then it can this structural component will not perhaps fail until a particular value of N, let's say, if this is the stress that is being applied in a cyclic basis. Again, all this depends upon what is the maximum, minimum, and what is the datum, because the stress that you're applying with respect to time is cyclic, in the sense that it could be with a datum which is 0, which is something like this, and this sigma naught that we are talking about is, let's say, this maximum range that you're looking at. Let's say it could be like this, or the datum could be such that this is the 0 of the stress, and this becomes the overall stress. It varies from 0 to sigma naught, and it could be positive or negative, the values of sigma naught. So based on all of that, this particular curve can change, and typically there's not a particular frequency at which these stresses vary. There could be a range of frequencies, and some way of accumulation has to be brought into picture. So all of that is not essential from your course perspective, but just to give you an understanding of how a cyclic loading could typically look like. With respect to time, you're essentially having your stresses varying, and when that is happening, the strength that is that the material is capable of, which is, let's say this is, for example, the ultimate tensile strength of that particular material. Let's say it's a brittle material like a composite. So then what would happen is, only when it's a static load, then that failure will happen at that stress. But once the load is time varying like this, because of that variation with respect to time, the strength starts dropping down, and depending upon what level of stress variations that are there, and also the datum, you could have the number of cycles determined through an experimental study. So these are typically experimental studies which can go on for sometimes months or years, depending upon the kind of material you have and the level of stress that you're dealing with. Especially if you're dealing with very low values of stress, it could go on for a very long period of time. So these are fairly expensive tests to perform, and therefore any insight through a theory or a modeling approach which is reliable enough is very, very advantageous here, because you may not be able to do away with the experiments completely, but after a certain level of experimental validation, you could do the rest of the things through, let's say, the theoretical model that you have, which you have validated for certain range of quantities. So that's the reason why in all situations, wherever if you have a reliable theory or you have, let's say, a computational model based on that theory, which is quite reliable, then you would prefer to use that and push the experimental testing to as much later stage as possible. It's not unavoidable, but in the initial stages when you want to validate the theory, it is required, and later stages in terms of the minimal certification requirements for an experimental demonstration is required. But in between, in terms of the overall development, companies use much more of experimental testing today than what is even required by the certifying agencies for greater confidence. But as and when better and better theories come into picture, then you would tend to start depending on them rather than the experimental test always as a brute force. So let's get back to this. So the fatigue response of the composite to the cyclic loading is what typically needs to be studied, and that's the direction in which we will touch upon as we move forward. Yes?
In case of metal and metal alloys, you know that if we load that, then unload that, strain hardening is happening. Do composites behave in the same way?
Again, it's a very large thing. So for example, if you're looking at metal matrix composites, for example, they would have, some of them would have strain hardening effect. But since most of the composites that we are talking about here for low temperature applications are polymer matrix composites, you typically don't have that. But there's a certain level of that happening when you go from thermoset kind of polymers, which is like epoxy, which is typically used, to what is being contemplated upon for quite some time now, and to some extent it's already been implemented, are thermoplastics, more from an environmental concern point of view. So in terms of recycling, thermosets are very, very detrimental to the environment. They cannot be recycled, whereas the thermoplastics can be, and therefore you're going towards that. But thermoplastics, for example, could bring in certain strain hardening effects, not to the extent that the metals would be, but to a greater extent than the thermosets. So it has to be looked at on a case-by-case basis, yes, but some of these concepts could carry over. So that's as far as the fourth F is concerned. The fifth F, as I said, there are dedicated courses in the department as well as especially in mechanical and civil, both regular FEM as well as nonlinear FEM, and a few other advanced versions of it. So those of you who are going to do research in this field and or need to do their projects, like the MTech project, for example, in that, might want to take that, because we will not be able to look at this in a very, very detailed way as is required for an actual implementation. It will be more from the point of view of when you're probably using certain commercial codes of based on finite element analysis. Are you able to understand the mechanics behind the model that you're employing for a particular element type that you look at? And are you able to, let's say, formulate the problem appropriately so that you can choose how to discretize the overall structure, how to apply the boundary conditions, whether it is the loads and or the way it is supported, and then eventually, of course, the final results, how you kind of interpret them, and from the post-processing, how you take it forward in terms of understanding. So the way we will approach this is just like in the fundamentals, we mentioned that along with the composites, FRPs, we are going to be looking at the consistent elasticity approach. In other words, the overall thing will be done with an elasticity kind of an approach, where you'll not be dealing with a particular, let's say, take only an axial rod at a time and take only the forces on either of its ends, tensile and or compressive, and the axial strain that is happening there, and relate them through the Young's modulus and the cross-sectional area. So that would be an ad hoc approach which is valid for just that kind of loading, that kind of a structure. Whereas when we talk of a 1D structure, we say that it could have an axial load, which could be either tensile or compressive. It could have a bending moment in one direction, it could have a bending moment in the opposite direction. These could be varying across the length, and the beam itself need not be prismatic. In other words, it could be tapered in both directions. And then apart from that, you could also have a torque which is applied in both directions. And that torque, just like the bending moment and the other forces that are there, axial force and the shear forces in both directions. So the transverse loading that is there, which causes the shear force, all of these could be varying along the length. And so all kinds of complications in the geometry distribution as well as material distribution also. Apart from using a composite which by itself is heterogeneous because of the fiber and matrix, you could have a hybrid composite, like the example that I stated in one of the previous classes. For many helicopter rotor blades, you would have closer to the root carbon fiber, whereas for the rest or most of the blade, you would have a glass fiber. And so essentially this is what we call as a hybrid material construction. We have more than one type of material. Within a composite it is hybrid, but letting that aside, because one of the ways in which we will tackle composites is through what is known as an equivalent homogeneous material. So in other words, it is a heterogeneous material, but we will think of or arrive at an imaginary material which behaves just like the other material as far as the overall structural behavior is concerned, but it has certain properties based on the properties of the individual component materials, which is the fiber properties, the matrix properties, their volume fractions, and if there are any additives and or voids, etc., depending on the manufacturing process, all of that, how it affects the overall performance. So this material doesn't exist in reality, but you have a way of handling things in a much more efficient computational approach. There are certain things this kind of a methodology will not allow you to do. For example, understanding the damage mechanics of this, because the actual damage could happen through a fiber matrix debonding, but now you don't have a fiber and a matrix in this imaginary material. You have the same material throughout, and that's a more complex material in terms of its math, because the properties are going to be different in different directions, even though the fiber by itself could have be isotropic, though there are a lot of anisotropic fibers as well. Many fibers could be isotropic in nature, and similarly the matrix is also isotropic, but because of the fiber geometry and its orientation with respect to the structural axis, you have the overall properties which are going to be anisotropic, and that imaginary material, what we call as the thanks. So the equivalent homogeneous material, whatever we have, that equivalent homogeneous material will have different properties based on the volume fractions and the different properties because of the orientation of the particular fibers, what we call as the longitudinal direction, and any direction perpendicular to that, which we call as the transverse direction. So we'll look into all of that in pictorially, as well as the equations derived, etc., later on. But the whole idea is that because this is a generic 1D structure, and similarly when you're talking of the skin of the fuselage or the skin of the let's say the wing or any of the lifting surfaces, the horizontal and or vertical tails as well, these are essentially, as we already saw, shell-like structures. For large aircraft, a lot of these wing panels, the initial curvature might be so low that even a plate model might work. But as we said, we are looking at shell in a generic sense, and then plate as a special case of that. Just like we can look at a curved beam and take the straight beam as a special case of that. And this is, in both these cases, you could have generic types of loading coming in. And because of those generic types of loadings, it's good to take this consistent elasticity approach where you're dealing with stresses, strains, not as scalar quantities, but as matrices. Of course, the most rigorous mathematical way of doing it would be to treat them as second order tensors and their relationship between them using a fourth order tensor. But we will not go into that in this course. It is part of other courses that we have in this department. But what we will do here is the best that we can do without complicating the mathematics. These second order tensors will be in the form of matrices, and those matrices based on certain symmetries, we will reduce those square matrices into column matrices, and we will relate the column matrices using square matrices again. In other words, even the fourth order tensor that we are going to have for the stress strain relationship, that is going to be reduced to a matrix kind of an equation through just a little bit of mathematical manipulation of the components or measure numbers of those tensors that are involved. So if you don't understand some of these terms, just don't bother, or you can note it down and ask me after the class. But in any case, we will be visiting some of these in actual column matrices that we'll be writing down, and therefore you'll be able to appreciate it at that point of time. But essentially, it's saying that we're not going to be dealing with these quantities as either scalar quantities, which is one end of the spectrum. That's how you deal with it in undergrad in the most basic strength of materials course, or as tensors, which is how it is appropriate to deal with in a research kind of a problem, whether you're doing your MTech project and or let's say even research as part of your PhD, or more advanced things like writing papers, etc. So typically you tend to deal with them as tensors. We are taking an in-between approach where we are trying to bring it in the form of matrices. So these will in general be multidimensional. So in other words, you have the stresses, the strains, and the constitutive law, as I said, as two sets of column matrices, and then one set of a square matrix which relates those two quantities. But in terms of the actual implementation of the algorithm and the code, it will not be in terms of strains, stresses, or even forces. There are also force-based finite element methods that some people, certain groups of academics and or industry also, who are into that because it has certain advantages of its own. But what we will be taking is a much more common methodology, which is very common even in the commercial codes as well, as a displacement-based finite element analysis, where at each node of this discretization that you have caused for the structure or structural component, you would use the displacement field at that point. Let's say start with a 3D displacement field if it's a 3D finite element implementation, and or a dimensionally reduced model for the 1D and 2D structures that we are more commonly going to be employing. But either case, it will be the displacement which will be the unknown, the only unknown. So how we go about doing that is, first of all, writing an expression for the strain energy, which is the energy stored in that particular structural component because of the work that is done by the external loads that are acting on the structure. Because of that external work done, there is a certain amount of strain that the structural component undergoes. But in turn, this structural component is attached to some other structural component. Let's say the skin is attached to the spars, and the spars in turn to the ribs, etc., which are all the skeletal components of the wing. We will look at each one of them diagrammatically later on. So the load is getting transferred. It's not all borne by the skin. So in other terms, when you're talking of the energy that is there from the work done, all of the energy is not stored in the skin because of the work that is done. That energy, part of it is through the deformation of the skin, and therefore part of the strain energy accounts for the work done, but the rest could be the deformations that the other components that are attached to it and then attached to that in turn, etc. They all undergo certain deformations because of that, and each one of them has a certain level of energy that it takes part in the whole process. So once we write that strain energy, the strain energy for a linear material, that is when the stress and the strain are related to each other linearly, the strain energy is quadratic in the strains, and that strain energy will be in terms of the strains, obviously by the very name of it, but we have what is known as the kinematic relationships, that is the strain displacement relationships, which are substituted into this, and therefore the strain energy gets known purely in terms of the displacement, and which is what we eventually minimize this whole functional, or what we call as the energy functional, with respect to after applying the appropriate boundary conditions, etc. So as I said, these equations that I used in the structural theories that you are familiar with, like the Euler-Bernoulli beam theory or Saint-Venant's torsion theory, etc., are taking one at a time these quantities, let's say only torsion applied, or only bending applied, or only an axial load applied in a bar, etc. When all of these are simultaneously present, how do you deal with the displacement is what we will try to understand. We will start with, of course, the structural theories to juxtapose it, and as part of how it's part of the bigger picture, 3D elasticity, to start with, to understand the various terminology that is typically used. A lot of this terminology you might be familiar from your strength of materials, but you might be using it in a discrete fashion, that these are separate individual problems, but we will see how they all fit into the overall construct of consistent elasticity, so that the understanding improves. So I think I've covered pretty much this. Any questions on this? Okay. Yeah, so the next is in terms of how we classify the various parts of flight vehicle structures, though we will try to do it in a more unified way. This is more of how other people tend to compartmentalize this whole thing and look at it in separate box approaches, and then try to fit things together. So as I said, there's no single basis. There are many different bases, of which I've listed a few over here, which are very commonly used, not only in textbooks, but also in the way computational codes are implemented, and or also the way some of the industrial teams are bifurcated in order to work on these different problems. One is flight vehicle structures purely based on the application. So what kind of flight vehicle are we talking about? It could be a fixed wing aircraft, in which case, again, there could be categorization depending upon what type of application it eventually goes into, the military kind of application and or civil kind of application. First of all, the fact that it is a fixed wing aircraft means that the wing is attached almost rigidly with respect to the fuselage. In other words, your cantilever kind of a boundary condition might be suitable for this. But as I already mentioned in a different context earlier, the 1D model will fail close to the point of attachment, and the actual way in which it is attached becomes important. And how close do you need to go is typically given by your Saint-Venant's principle itself. It's of the order of your cross-sectional dimension. So your cross-sectional, at the cross-sectional of the root of the wing, the chord, that would determine approximately about one chord away from the point of attachment, or the mean point of attachment, if the attachment itself is a fairly complex structure. So then about one chord away from the root, up to that point, 1D models can give you very, very accurate results. But once you go closer than that to the root, then you do need to do a 3D kind of a finite element analysis in that region. So the reason why a helicopter, for example, it would be quite different to analyze from aircraft would be because now you're having a rotating structure, and the way the helicopter rotor blade is attached to the hub could be different ways. Some of the first few helicopters, and also some of the designs which are even in the recent past, but more low-cost helicopters, are what are known as fully articulated, having fully articulated blades. So in other words, they will have a hinge which will allow it to flap like this about a certain axis to certain degree of freedom, and then you have another hinge which is essentially what is known as a lead lag hinge, and then there will be a third which is not a hinge but a bearing, and about that bearing you can actually undergo a rotation. But once composites came in, we wanted to minimize the number of parts and avoid these joints. We took advantage of the fact that these composites are very flexible in nature, and therefore something similar to elastomeric bearings. Just like if you fold your book, you see that hinge that is there across the pages, you have a certain small level of stiffness that is essentially there. So it's an elastomeric bearing, like what we call that. So essentially what is happening is, it's like a cantilever, but the stiffnesses for an actual ideal cantilever fixed end would be infinite stiffnesses. But here what you're talking about is a very large stiffnesses, but essentially allowing for a little bit of flexibility. So the kind of models that you would use for an aircraft wing, the way that is attached to the fuselage and the way the helicopter rotor blade is attached to the hub are quite different, and therefore there will be subtle differences in how the structural modeling will be done there as well. Why is it so different from the application point of view? Whether it's a military aircraft or a civil aircraft, if both are fixed wing, how should it matter? The idea is that we have to start with the loading, and for which the VN diagram becomes very critical. That is, when you plot versus the speed which is the airspeed, equivalently is the speed of the aircraft, how it changes, and what is the limits as far as the load factor is concerned, which is defined as the lift divided by the weight of the aircraft, which for cruise is 1. But when you're doing certain maneuvers, it could become much larger than 1, or it could even go to 0 and or negative values. So within that range is what we are trying to model, and for military aircraft, typically that spread will be much more, especially as far as the end direction is concerned, and also if it's supersonic kind of fighters, and as we move, maybe we'll talk about the other aspects like missiles, etc. But essentially what you're talking about is a larger range of speeds and larger range of load factors n that is it has to undertake, and therefore the structure has to be designed according to that, and therefore the structural components, that is the spars, the stringers, longerons, etc., also have to be decided according to that. And another typical difference is many of the civilian aircraft, except for a few exceptions like the Concorde and a few other things that are being developed like the hyperplane, etc., most of them are in the transonic regime, and therefore the kind of airfoil cross sections are much simpler to deal with, whereas in terms of the structural analysis and also the design, because they don't have very many sharp edges except for the trailing edge, which is anyway not going to be loaded too much. So it's the rest of the airfoil cross section which is going to be loaded. So even when you go to supercritical airfoils, etc., there's not too much of a complication. Whereas you might have delta wings in the case of military vehicle, that's in terms of the planform, but in terms of the airfoil cross section also, you could have sharp edges that are coming in even where it is strongly loaded. And sharp edges are always a problem as far as structures is concerned, because stress concentrations can result over there. And one of the things we looked at earlier is one of the F's is the fracture mechanics, and that will play a critical role when you're dealing with such kind of structures. Another case where this really became very important is in civilian aircraft, when the window shapes were being decided upon. The earlier windows were all rectangular, and typically cracks originated at those corners, and people later very quickly, of course, found out that what is the issue over there, and therefore if you might remember from your flights that you typically have rounded edges now, almost an oval shape kind of a window. And also in terms of the stiffening, there's also a doubler that is put up typically on the window frame. So the way the window is glass panes, it's a laminated glass structure, of course, and there's a certain level of heating, etc., which are involved. The window design itself is a fairly complicated structural design, because a certain level of transparency that you need. While the aircraft is operating at different altitudes, you still need that level of transparency to remain, and still the internal pressurization is there. That is going to cause certain hoop stresses and longitudinal stresses, and it should be able to bear all of that. And then, of course, it has to transmit that load to the rest of the fuselage structure, and that is usually done through what are known as doublers, essentially frames into which the glass is actually fitted. So the reason I'm giving these few examples and nuggets here and there is to show you that even though these might look like non-structural related aspects, it does affect the decisions that a structural engineer makes.
Spoke about the elastomeric bearings on how the rotor blades are made. But in that case, we use the control of the angle, right? So we won't be able to control it because then it is just dependent on what load is coming and how the structure.
Yeah, very good question. So the question is about the elastomeric bearings and how the control can be affected, because the rotor blade it can probably move by itself. Yes, to some extent it moves by itself, but there's what's known as a swash plate mechanism. The swash plate mechanism is a way through which the hub is connected to the rotor blade, and this swash plate mechanism, through that the controls of the helicopter pilot are connected. So in particular, the stick that he or she is using, so which can be moved forward or backward, just like in a fixed wing aircraft, and to the left or right. So what happens in this case is there's a fairly complex aerodynamics happening, but from the pilot's perspective, it is quite intuitive that when he's trying to push it to the left, the helicopter is yawing to the left, but it has to be in conjunction with your rudder pedals, because just like in the fixed wing aircraft, the roll dynamics and the yaw dynamics are connected to each other, and the sideway drift as well. So when he or she is using the rudder pedals, what happens is that if it's a conventional kind of a helicopter, you're having a tail rotor. So the tail rotor is primarily there for anti-torque. So in other words, according to Newton's third law, if the rotor is rotating in one direction and you don't have a tail rotor or any other such mechanism, the helicopter is going to rotate in the opposite direction. So to avoid that, you have over a moment arm, which is called as the tail boom. At the end, you fit a tail rotor so that the thrust that tail rotor is having is the sideway force, and you're essentially controlling that through the rudder pedal. So you're doing this as well as that. So what happens when from the pilot's perspective, it's quite intuitive that when he moves it forward, essentially the rotor plane tilts this way. Earlier we talked about in a fixed wing, we compartmentalized just like the Wright brothers, the thrust and the lift. This is one place where both are combined again. So both the lift as well as the thrust are for a helicopter are provided by the main rotor. So the main rotor, what happens is essentially it is tilting forward, but that is not tilting by tilting the hub, because that will require an enormous amount of energy to do that, and it will be a very inefficient way of controlling. So we tend to ingeniously utilize the aerodynamic coupling that is happening between what is known as a flap motion. Now, because we have done away with the hinge and we are using just ply drops to make it a little more flexible over there, almost like a hinge, but a hinge is zero stiffness ideally, but this is low stiffness that we are trying to do. So what we are trying to do is, this is a flapping motion which is allowed, and there's a lead lag motion which is allowed. Now this flapping motion, and there's also, because of the bearing, there's a pitch motion, right? And even if it's a bearingless kind of a configuration, there is, through this swash plate mechanism, there are small levers which come over here, and you can push up the lever or pull down the lever. So accordingly, this rotor blade will change its angle of attack. So the pitch is changed, which means the angle of attack is changed. So what actually happens is that, very interestingly, it can be proved through rigorous analysis, that this flapping motion and the pitching motion are related to each other. So in other words, if I tend to, let's say, increase the pitch over here, the flap will also be affected by it, but the flap will not increase at this point. There is a 90-degree lag behind it. So when the blade comes to this location, that's where the flap will increase. So in other words, the actual intuitively, the pilot sees that by moving it forward or backward, he is making the aircraft move forward or backward, the helicopter. But in reality what he's doing is not doing it at the front or back, but he's doing at the sides. What he's doing is to move backwards, let's say, he's increasing the pitch over here so that the flap is increased here. He's decreasing the pitch over here so that the flap is decreased over here. So essentially the rotor plane is tilted slightly backwards. So it does offer the lift, but it also offers a thrust, which is a backward thrust, and that's why you see helicopters can move backwards as well, just like they can move forwards or sideways. So in other words, the control is still there. It's just that the way we take advantage of the aerodynamic couplings in order to do it, it's still fairly efficient even without the bearings and the hinges. But the greater advantage is that you have fewer number of parts. The maintenance schedules are much lesser for a composite. In terms of replacement of parts and things like that, becomes much more effective overall cost reductions. Though the initial cost of a composite rotor blade might be more, over the entire life cycle of the helicopter, the replacements are much lesser and you therefore save on it. Yeah. Yes.
Some particular helicopter models are there where they do not have tail rotor.
Excellent. Yeah.
They have two instead of the
Right.
main rotor.
Right.
How
Right.
they are getting anti-torque and
Very good question. Yeah. Yeah. So essentially, there are many different multi-rotor configurations. We don't call the tail rotor as a multi-rotor because it's an additional rotor that we are looking at. When you have more than one main rotor, we call it a multi-rotor configuration. So one example of that could be counter-rotating rotors, which are on the same hub, but they are rotating in opposite directions. So one is creating a torque in one direction, the other is creating a torque in the other direction. So they're essentially balancing it out. So the fuselage is not affected by that torque. Okay. So another is essentially a tandem or side by side. So side by side is when you're having on two for very large helicopters, some of the Russian helicopters you might have seen. So you typically have these side by side, and once again they are rotating in opposite directions. Now this has to be controlled in an appropriate way because they may not be as far apart as the radius of the rotor blades. There might be in between going. So that is appropriately taken care of in terms of how you pass the motor signals to the helicopter rotor blade, each of those rotors. So it's controlled in an appropriate way that they don't clash with each other. But essentially, once again, it's creating torques in two different directions, equal and opposite, so they cancel out each other. Same thing with the front and back as well, the tandem kind of a configuration.
when they change directions or move sideways, that way they changes the configuration of two main rotors. The flap will be changed in two main rotors.
Exactly, exactly. So the control system will take care of that so that it's kind of distributed. Right? It's very similar to in a fixed wing aircraft. When it's, let's say, taking off, you need a much larger lift coefficient. So you will deploy the flaps. So the flaps will generally be deployed by an equal amount on both your left and right wing, unless and until you need some kind of yawing that is required along with the roll to change the direction. But otherwise, if it's in the simplest kind of a takeoff that you have, you would deflect both the flaps by the same amount. If you don't, then there is a possibility of the lift on one of the wings being more than the other, and therefore a roll happening undesired manner. Right? There's also one more configuration for helicopters, since you brought that up, where you do not have these multiple main rotors, and you still don't have a tail rotor, and you still can take care of the anti-torque. Anybody has seen that kind of an example? Remember? Okay. Okay. So essentially, this was done. I think there might be a few others in the after that time also. But one of the first which did that was by a company called McDonnell Douglas, which was eventually taken over by Boeing. So it's part of the Boeing family now for many decades. So they came up with a configuration called, in fact, I would have probably written that. Yeah, this one. NOTAR, no tail rotor. So the no tail rotor, how it works is that it also has a tail boom like conventional helicopters, but at the end it doesn't have a tail rotor, but it has a way of exhausting that the stream of air. It's essentially an air stream which is there at the one end of the So essentially what is happening is this is let's say the tail boom of the helicopter. So here there's a high-speed fan inside the tail boom, which is having a very large speed air coming out of it. And on one side you have an opening to either the left or the right depending upon the design, and that air stream comes out of it. So it's very similar to a rocket engine where you know that the thrust is essentially through the exhaust velocity that is because of Newton's third law. When the air is coming out, it pushes the aircraft in the opposite direction. So that's essentially offering your sideway force just like the tail rotor, and therefore handling the what is coming from the main rotor, whatever torque is coming because of that. This is essentially the torque coming because of this about the CG of the aircraft is going to be in the opposite direction, and therefore they're going to balance each other out. Yeah. So that's as far, yeah, and typically when you're looking at smaller aircraft like business applications and or sports, once again sports, a lot of things will be in terms of the maneuvers that are required, and therefore larger range of N, that is the load factor would be considered over there. Business, it's more in terms of the distribution, the layouts that you have in the interiors, and therefore how that configuration helps, and it's typically short haul, and therefore the cyclic loading that is there in terms of takeoffs and landings might be much more involved, so therefore the fatigue has to be accounted for. So there are many different subtle ways in which the actual mission profile can affect the structural designer's thought process and the design decisions as well. So helicopters, and typically missiles, you could have the surface to air, the air to air kind of missiles, air to surface, depending on each one of them, the kind of regime in which the mission is accomplished, the kind of loads which come on the structure could be quite different. Some of these are shared with the launch vehicles as well in terms of the kind of structural loads. Many of these are kind of rocket engines in which are, let's say, solid propellant. They typically have a filament wound kind of a casing if you're looking for composites, and typically you have at the end what are known as polar bosses. So these are attached at the ends, and the polar boss design is a very intricate thing, how what kind of loads come on there and how the thickness changes from the cylindrical portion as it thickens out to the edge, because there has to be an opening for the exhaust to come out, which is what creates the thrust. So all of those things will come into picture in terms of understanding, and because it gets so thick that your shell-like models will not work over there, you might need a 3D finite element analysis, and the transverse shear will become very important over there towards the end of the polar bosses, the way these are typically designed. Again, depending upon whether it is what kind of the launch it is for either a polar orbit and or a geostationary orbit, you might have certain different requirements because the range of loads that come in would be quite different, and that will impact the structural decisions, or sounding rockets, for example. Then coming to satellites, again, of course, depending on the orbit in which they are, they might be affected by one or more planetary bodies. For example, if it's a geostationary satellite, there might be times when it is affected by the moon's gravity also as much. So you have to account for those kinds of loading situations as well. So that's essentially how many of these things differ. But there's even more when you get into re-entry modules and things like that, because the kind of heating that happens when these modules enter back, the thermal loads are really massive, and because it has to be designed to operate both in the atmosphere as well as in the space of pretty much vacuum conditions. So the range of kind of loads that you have, similar to the flight envelope we talked about in the aircraft, but much larger ranges that we are talking about, both in terms of the velocities as well as the load factors that are involved. And in addition, as I said, the heating that happens during the re-entry process and the kind of thermal insulation that you have, the kind of active cooling systems that you might have to have, the tiles that you might have to have, all these kinds of things, many of which the structural engineer plays a part in understanding and making these decisions as well, along with a few other team members. So again, I think within the any of these categories, depending upon whether the aircraft is subsonic, supersonic, or hypersonic, again, we discussed in terms of the airfoil configurations, the platforms, they are different, and therefore the interior structural configuration will also be quite different when we go to that. So that's purely based on the application, but the primary design principles and or structural theories remain the same. It's just that extent to which you might have to consider certain types of extreme loading situations is where the thing matters. Coming to the engineering stages, once again you have it could be an analysis kind of a problem where you have an already existing aircraft, so you know its geometry in terms of each structural component, how large it is, where it is extending from to where, how it is joined to the other structural components. So you know the loading conditions, the boundary conditions, everything. You just want to determine what kind of stresses might occur in it, what kind of deformations might occur in it, how it transfers that to the other structural components. So those kinds of problems you typically have, which is the almost run-of-the-mill straightforward things. But when you go to design, essentially you don't know these things. You're trying to arrive at the geometry of the, let's say, spar. So you're trying to design that spar. You want to, first of all, from the overall aircraft design, the preliminary design, you have the data from the aerodynamicist for the span. So based on which you know approximately you account for the fuselage width at the points where the wing is attached. So you know the length of the spar that you probably need. But then how many spars you want to have? Do you want to have a single large cross-section spar, or do you want to have, let's say, 2 or 3 spars of smaller cross-sectional area? And each one of those spars, what kind of cross-section do you want to have? Typically, because most of the loads there are bending, you might end up with an I section, which is fairly common, but that need not be the only option that you have. So the and again, in terms of the spacing of the spars, if you have multiple spars, how far they are apart from each other, that will also matter. Within the I section, what is the flange cross-sectional area you want to have? Do you want to have the same flange cross-sectional area, top and bottom? Many cases you would see there is an asymmetry there as well, because the kind of loads that the upper portion is, upper flange of the spar is subjected to is mostly compressive, whereas in the actual flying conditions where there is a non-zero lift, and typically the lift is much more than the self-weight of the wing and or its contents like the fuel tank and things like that, which provide a certain relief, or the engines being attached to it. So essentially the top portion is going to be under compression. So for example, the stringer design, the stringers are longitudinal stiffening members which run along the length. If they're much longer, they're typically called as longerons. So, which if it runs through shorter distances, it's called as stringers, but essentially it functions in a similar way. So what it is taking is the compressive load if it's on the top, and it's if it's on the bottom, it's taking a let's say a tensile load. But on the ground, of course, because of the self-weight of the wing, which is much lesser than the lift, because the lift is comparable to the weight of the aircraft, or much more than that if it's at maneuvering or having certain load factor which is greater than 1. But as far as this is concerned, on the self-weight of the wing is a smaller portion of the overall aircraft weight, and therefore that is not usually so critical. But the loadings get reversed. The bottom is under compression, the top is under tension. But the critical compression is on the top and the critical tension is at the bottom. So the kind of stringers you might have would be such that, for example, on the top, you might choose what is known as a hat section. So essentially, you're having, let's say, the airfoil cross section. So you could have something which is the size is exaggerated over here, but essentially you see what is happening is that cross section of the stringer is essentially something like this, which is essentially hat. You could have, if it's a metallic structure, it could be typically riveted over there, and if it's a composite structure, you could have adhesives and or along with it. So the way it is attached. So a design like this, what it could actually help in is that in the compressive load, it's not just the material failure which could occur, but also the possibility of elastic instability or buckling that can happen. So you would want to avoid that. So essentially what you're looking at is a structure which can provide sufficient amount of, along with the skin, of course, because along with the skin, of course, it's essentially a structure which has reasonable amount of torsional stability because it's a closed structure and it's spread apart sufficiently. So essentially you're talking about a compressive load that is happening on this, and therefore it should be able to avoid buckling. As I said, the skin can be allowed to buckle. The skin might buckle, but you don't want the stringers to buckle because the load from the skin is getting transferred to the stringers, and that in turn to the ribs and eventually spars, etc. But you want to ensure that you have something like this. Whereas in the bottom portion, you have stringers which are something like this. Let's say a Z section that you have. So it's a Z shape that you have. It typically is called. So you might be having rivets and or adhesives over there to attach that. So it's okay. It's an open section compared to this, which is a closed section, but it's still okay because this is primarily at the bottom surface. It's going to undergo tension. There's no problem of, let's say, the buckling or any other elastic instability coming up over there. So why not use that hat everywhere on the top as well as the bottom? What is the advantage of using certain open sections where it is possible, where compressive loads are not much? Anybody? Okay. Yeah, that's one of the reasons. Again, it depends on the symmetry or asymmetry of the structure and the actual section. So it's that's a possibility, as you said, the shear center could occur outside. But there's another reason, typically a non-structural reason why, where it is possible, you would want to avoid this kind of design. You might still use a hat structure at the bottom, but you might put the hat like this instead of, and rivet it over here instead of the other way around. Why? Huh? Come again? Yes, very good point. So essentially, in terms of fitting and accessibility, it's one thing. Also, to extend on that, in terms of maintenance, when you're trying to do inspections and things like that, you open up a panel on the top, much more easy to inspect these, whereas it becomes a little more difficult to inspect that. Again, we're talking of in a very generic terms, but you can have this kind of a design in which inspection is possible by appropriate placement of the panels and the panel openings that you have and things like that. So there are various ways of working around this design. But essentially what we're talking about is various different cross sections are possible, and the choice of that cross section that you have to do, we are essentially talking about it from the point of view of design. One is in terms of the choice of the number of spars, then the choice of the cross section for the spar and for the stringers, how far away they are spaced from each other, what material is being used, etc. So in a sense, the design is also like an analysis problem, but you're doing it in an iterative fashion, and there's an optimization that is eventually involved. So which means that you might, the simplest way of looking at it is you're essentially running the analysis over and over again. So it's a much more involved process over there. And that's why when you're talking about these two different ways of analyzing problems, one is using a 3D model, finite element commercial software. The other is using dimensionally reduced models like a 1D and or 2D for the skin using a 2D, and for all of these beams using a 1D kind of a model. The time savings that are there may not be very clearly evident in the case of an analysis problem, because you may not be doing it on again and again on a routine basis. But when it's a design problem, this makes a huge difference, and that's why big companies or companies which have been around for a long period of time, like Boeing, and to some extent Airbus as well, invest so much into R&D, because if they have this advantage of a more reliable dimensionally reduced 1D or 2D model instead of an they have capabilities of, you could have of the order of millions of degrees of freedom, where you consider the entire wing structure loading, you could probably analyze. But you would want to do that at a much later stage in terms of a detailed design. Eventually everything is close to completion. Very small minor changes are required, and you want to have far more accuracy. You might do a full 3D model for the entire wing. But wherever it is possible, you want to break up the overall structure. You know the boundary conditions in terms of the way they are attached, and therefore how the load transfer takes place between a stringer and a skin, etc. And therefore individual designs can be done using dimensionally reduced models. And there the design can sometimes mean a few years. For example, let's say this didn't happen, of course, but for example, if Boeing was developing 787 Dreamliner and and Airbus was developing the A350 extra wide body, and let's say they started at the same time. In reality, of course, the Dreamliner design started much earlier. But suppose they were starting at the same time, and let's say one of the companies, the A or B company, had the advantage of dimensionally reduced models, they would probably bring the aircraft to market much quicker, and therefore huge advantage in terms of capturing a lot of the market, because the repeat buyers are going to be much lesser, and in these kinds of things where a large amount of investment is required. So typically whoever comes first has that advantage. So it's very important that these have repercussions, though they might look purely a structural or a geeky stuff from the academic perspective, but they have implications in terms of how the overall industry functions.
So the bottom portion of the airfoil is primarily tension.
Uh-huh.
Why would we put a reinforcement bar?
Yeah, good question. So it's because if you want the skin alone to take it, if you don't put any reinforcement, the skin should take all the tension, right? So the kind of tension that is involved because of the large bending moments in a large aircraft which is flying fast could be so much that the thickness of the shell that is required is very large. So when you let's say instead of having let's say a 10 mm thickness, if you go for 2 mm, but you put the rest in the form of stringers, the overall weight of that stiffened structure typically turns out to be optimized appropriately and spaced out properly, will turn out to be it will be much more efficient kind of a design. What we call as a semi-monocoque design, where it's a stiffened design as opposed to just the sheet alone. Because you think of it, it's just let's say you start with an aircraft which is designed to be a small aircraft flying at low speeds, and slowly you become ambitious as a design company. You want the aircraft to travel at much larger speeds and or carry more payload or take more fuel for a larger distance, whatever it might be. Essentially the stresses are going to increase. So therefore the thickness required of your bottom shell is also going to increase, so that material failure doesn't happen. You're right that the elastic instability is not much of an issue, unless of course on the ground the self weight of the wing itself is causing that buckling, which is very rare situation. So if you have designed it appropriately, buckling and things like that will not happen, but typically your material failure will happen. To avoid that, to keep the same levels of factors of safety, once you have faster and or larger aircraft, you will tend to increase the thickness of the bottom skin. And therefore the weight penalty that comes just by increasing the skin alone and keeping it unstiffened is much more than bringing in the stiffener. So this is essentially a decision which is made based on comparative thing. So it's not that it's impossible. There could be a certain range of speeds and or sizes for which what you're saying is absolutely true, that in very low speed subsonic small aircraft, you could have even the top surface unstiffened. As you keep on increasing these requirements, both in terms of weight and the speed, then you might reach a stage where stiffening is required only for the top. But then most situations that are there are situations where even the bottom starts requiring it, because otherwise the structural efficiency goes down.
So, but when it comes to tension, it is the cross-section area that matters, right? So, rather than
That's correct. That's correct. So you know that, see, it's also the distribution of the load. See, the kind of pressure distribution that happens on the bottom surface, and also the kind of attachments that are there, the loads which are coming because of that, etc. So you know that the entire wing, both in the spanwise as well as the chordwise direction, may not have the same kind of stresses. One way of overcoming that in an unstiffened design is to have a tapered thing where certain regions are thicker, certain regions are thinner, so you could still have a metal sheet, for example, or even a composite where there are ply drops which are designed appropriately. So that is one way of designing. So it's not that it's ruled out, but conventionally the way people have approached it is by seeing wherever the loads are more, you try to put these stiffeners, so that in regions where you wanted larger thickness, instead you have a stiffener rather than making the skin itself change its thickness. Overall, you have the minimum required thickness of the skin, and then you put these stiffeners wherever the attachment points might be, and or a few other loads might be coming in a concentrated way. In fact, the word concentrated is more of an idealization. There's no such thing as an actual concentrated load. However, even if it's a needle point that you're talking about, it's not a zero area that you have of a needle point. You have a very small area, so that the intensity is very large. In other words, the force divided by area is very large, but it's never infinite. So these are purely from a theoretical modeling point of view. We talk about concentrated loads, but essentially you're talking about typically low intensity loads and high intensity loads, and those high intensity loads are the locations where you would want these stiffeners. And those stiffeners could be not only these longitudinal kind of stiffeners, but also the transverse kind of stiffeners, what we call as ribs in the case of a wing, and bulkheads and various forms that you could have for the fuselage as well. For example, there's a rare bulkhead where the empennage or the tail is attached to it. Where the wing is attached, you might have a fairly large cross-section frame that is typically used, etc. Right?
integral stiffness in the sort of.
Exactly. In fact, many of the composite designs, one of the advantages that you have is that you don't need to go for that, and you can integrally manufacture. In fact, a few metal aircraft also, they have tried to do that in terms of extrusion processes. So instead of having, let's say, sheet metal and then attaching through rivets, you would have extrusion process if the model is not too overly complicated and can be done through extrusion. That is a very, very big advantage if you can integrally manufacture. In the composites industry, it's called co-curing. So essentially you're co-curing, so that usually, because most of the failures originate at the joints, they become the weak link of the overall structure. So if you can integrally manufacture wherever you can, the technology is available and you can handle it, so you would prefer to do that. Yes. Yeah.
So what is the guiding criteria for designing the stiffness and stiffness? Because, for example, if we talk about conventionally beams or columns, but columns we generally design it for an actually compressive load-bearing member.
Yeah.
But in case of stringers, depending upon the varying angle of attack, they are going to face different kinds of loads.
Correct.
All flexural conditions, axial conditions,
Yeah.
torsional conditions, all of them are they are going to face.
Correct.
Then what is the guiding criteria?
Yeah. Yeah.
How
So,
will we
right. Just. Oh. So we have what is known as a VN diagram. Okay, so essentially this is the true airspeed or equivalent airspeed that of the aircraft that you would have, typically abbreviated as EAS. And this is essentially your load factor, which is defined as the lift divided by the divided by the weight. Okay, so in a cruise, oh, I see. Thank you. Yeah, so I can write with this. Okay, fine. So this lift by weight in cruise kind of a condition is one. Okay, but in other kind of situations, it's not one. So typically, in terms of the lowest speed for fixed wing aircraft, unlike a helicopter which can hover or even fly backwards, there's a lower speed limit that you have, what you typically call a stall, because of which there is a quadratic boundary line over here. And similarly, there's a negative angle of attacks also. There is a similar quadratic thing that you could have over here. And typically, you would have a certain N max that you have over here, and similarly another N in a negative sense, there is an N max also, and we'll go into some of these. Oops. Okay, anyway, so something like this. So you have a certain N max over here. Typically we call this as the dive speed. Okay, and then this is of course the let's call it N minimum, or the maximum in the maximum in the negative sense. And essentially this gives you the flight envelope. This is called as the flight envelope for the entire aircraft. And for different types of aircraft, there could be slight differences in how it comes. We will talk about these chamfers and other things. I'll not go into the details right now. But essentially, if the aircraft is flying within this particular envelope, then it is safe. If it goes beyond this in any one of those directions, there is a problem. So this is essentially a stall. Here there could be a material failure that happens because the N is so large, therefore the stresses are so large, it approaches the tensile strength or whatever of that at least particular structural component, so that it will fail. So essentially that's essentially happening, and there's a maximum speed that the aircraft can fly out of, again determined by the aerodynamics, and probably you'll study that as part of the aerodynamics module in your flight and space mechanics course. Keeping all that aside, we get, as structural engineers, we get this as an input. Okay, so for a given aircraft, and based on that, we see all these points are like extreme points that we need to consider. We will check for all of these points. Suppose that value of N and that particular value of the V that is there for at any one of those given points. What is the V value? What is the N value? We would check what is the kind of loads that are coming, and therefore what are the stresses in each one of those individual components. So for a particular component, one of those might become more critical compared to the other, and you have to ensure that if it is designed for that, all the others are taken care of as well. So that is essentially how the approach is done. Does that answer your question? Yeah. So angle of attack. So essentially what you're doing is, see, for example, if you plot what is known as the lift coefficient of the entire aircraft, which is its lift divided by the dynamic pressure in so some reference area of the wing, which could be the planform area of the wing, for example. So when you plot this versus the angle of attack, you typically, depending upon the camber, whether it is cambered or not, let's assume it's not cambered, so it will have a particular CL even when alpha is 0. So you would have, let's say, something like this. So essentially this is in your alpha stall that you're talking about. And you could have similar thing on the negative side as well. So when your angle of attack is changing, what is happening is your CL is changing, and therefore essentially depending upon how the pilot is controlling that change in angle of attack through the other controls and all the thrust as well of the engine, etc., the velocity can be independently controlled to some extent. And therefore, you might, once again, what it will essentially give you is that as you increase the alpha, you're essentially moving towards this particular curve, and or you're decreasing it, essentially you're moving towards this particular curve. So you're still taken care of as long as you have designed for these limits, you have taken care of for the different ranges of angle of attack that you might have. Yeah, it's a very interesting question. It has to be a dialogue between them. So it will go through a few iterations typically. So the initial thing will come through your flight design team, which is essentially talking about what is the mission profile. So based on the kind of maneuvers that might be required, etc. So for example, for fighters, etc., you might define certain kinds of operations that it might need to undertake. Based on those operations, what are the maneuvers which are involved, and therefore you arrive at the Nmax. But then it goes through a few iteration process until the detailed design happens, but the initial iterative value comes from the design team. I think so. Maybe you'll know better.
Once this flight envelope is established, we may just maintain the
Right,
operation.
right.
We
Okay.
have something called as operating limits, which is much lesser than this flight envelope.
Okay.
Not exceed values for
Right. So essentially a form of this which is not as extreme as these limits, but somewhere in between, so that they'll be aware of what are the risks not to cross. Yeah. Yes. Okay. Yeah.
Why does the end decrease just before reaching the peak?
You mean this? Yeah, I'll come to that because it has certain structural repercussions to that. I'll have something. So as I said, certain questions I'll not answer because I don't want to break the suspense of that. So in fact, even the Venn diagram, I'll probably bring it up in a little later context. Just because the question was associated with that, I tried to bring it up in that context. But essentially, it's talking about when you're reaching the maximum speed, you may not have at the same time the possibility of having an Nmax as well. So it's very similar to, let's say, in a structural material, if you're loading it in only one direction, there is a certain ultimate tensile strength. So now if it's a bidirectional load, you're loading it in this direction. Let's take this tabletop, for example. If I'm trying to pull it along the length, it will break at a particular stress. I'm not applying any load on this side. But if I'm simultaneously pulling it along that as well as this, it might break at a stress which is lower than the ultimate tensile strength in either one of these directions. So that is essentially what we are talking about. So you might not have, this might become too critical to design. In other words, from a structural point of view, the structural weight required to cater to that kind of a requirement might be very large. Okay, there are other reasons for the chamfer as well, but I'm telling it to you purely from a structural point of view that extreme you want to avoid because it brings in unnecessary weight penalty, and because most of the time you're going to be operating at some V cruise at n equal to 1. At some location like this, you're going to be operating, okay? So unnecessarily by over designing it and stretching it to that particular point, the weight that is required might be so high that it's not worth the thing, because in these regimes you'll be flying very inefficiently. Yeah, so I think any other questions related to this? I'll erase this otherwise. So let's look at this. Yeah, analysis and design. The other thing that we talked about is stability kind of problems, not just structural stability, but also the overall vehicle stability aspects. Associated with that is in terms of the controllability as well. So when the control surfaces are deflected, the kind of aerodynamic pressure and shear distributions are different over those surfaces, so the way it behaves is going to be quite different. For example, we just plotted the CL alpha curve that is going to change once the control surfaces are deflected, and the way the loads are going to come because of those deflections are going to be quite different as well. So from a stability and controllability point of view also, you could have many different engineering problems coming to the structural engineer as well. Another thing which is becoming almost mandatory for current designs is what is known as a HUMS system. Health and usage monitoring systems. So this is not just for the structural health, but also all the other systems that you have in the aircraft or any flying vehicle. How do you explore the current status of health, and also sometimes in terms of prognostics, how it might deteriorate over a period of time, and therefore is there any change required in the maintenance schedules, etc. So these kinds of things are typically done by that. As a precursor to the HUMS system was a purely structural health monitoring system, what is called as an SHM, structural health monitoring, was a technology that was being used for a long period of time. Now, slowly for most modern aircraft, SHM is built into as a part of the HUMS system itself. There's a level of diagnosis which is involved, which includes visible inspections, which includes the non-destructive testing, and based on that testing and non-destructive evaluation. And once that diagnosis is done, some prognosis in terms of the life estimation, how much longer it might last, and how you could probably extend that life beyond that by engaging in certain repairs. For example, you find there's a crack happening. Instead of trying to address that crack alone, typically what will be done is there'll be a cutout made around that crack, and a patch might be put up, typically a composite patch, for example, which can therefore ensure that structural the integrity is still maintained for a slightly longer period of time. So again, each one of these is a fairly involved kind of research and the technology based on that, and some of these are proprietary to the kind of maintenance schedules which are associated with individual aircraft and or companies making those aircraft. So that's extending the life of the aircraft. In terms of understanding the damage mechanics itself, in the case of metals, there's a complication that occurs because you're going beyond yield into the plastic regimes, and you have to see how it behaves in those plastic regimes. In the case of composites, the number of modes of damage could be much more. I've listed it out earlier also. So in terms of fiber breakage, the matrix cracking, the fiber and matrix debonding from each other, delaminations that could occur, etc. So many different possibilities are there, and when one of them occurs, the other could also be incited over a period of time. So in other words, there's a complicated mechanism through which the damage growth happens. One is the damage initiation, the other is the damage growth. A lot of this can be studied as part of fracture mechanics, not directly applying what you understand from metals, but developed in particular for composites. The terms remain similar, but the way in which the behavior changes as the damage progresses is quite different. This is of course something peculiar to it. Of course in metals also, when you have joints like lap joints or butt joints, etc., you have an interface between two layers. So to some extent there is an understanding of how the interfacial properties, the contact mechanics, etc., develop. So some things are carryovers, but a lot of things have to be developed separately for typical aerospace composite structures. So that's as far as the on the basis of engineering stage, how we distinguish these things. The next thing that we will talk about is in terms of time dependency also, the dependency of the problem that we are talking about, whether it depends on time or not, it's statics or dynamics, and if it does depend on time, what kind of dependency is there. It could be a regular vibration kind of a problem. Typically we study free vibration because that is helps us characterize the structure along with its material and geometry in order to understand the eigenfrequencies, eigenmodes, to see what are the kind of initial set of modes that you have, whether they are associated with a particular kind of behavior like flexural alone, or it's a coupling between flexural torsional or flexural axial, etc. So those kinds of things give a lot of insight when you're actually studying the actual kind of problems faced by the structure through a forced vibration in the presence of external loads, how the structure is vibrating. The free vibration study that you have done will feed into understanding that forced vibration in a better sense. And you could have situations where there are random kind of loads like turbulence, air turbulence, you might have the gust loads, etc. And so you might have to be prepared for random kind of vibrations as well, which typically involve certain weightage of the various modes that you have already studied as part of the free vibration problem, but not as clearly demarcated in the forced case, but a little more leeway that you give. Again, what we talked about in terms of non-deterministic designs into bringing in certain probability density distribution functions, etc. Those things will come in handy over there. That's as far as vibration is concerned. The second kind of dynamic loading that we, I think, discussed quite a bit earlier was in terms of the impact kind of problems. The other is fatigue, that also we talked about the SN curve, etc. So depending upon how this time dependency is there, all of these helps. But most of the course will be focused now on statics, and as I already explained to you earlier, this is not just a textbook kind of an exercise, an academic exercise. It really feeds into the cross-sectional analysis of a beam and the through the thickness analysis of a plate or shell, even for dynamics problem as complicated as impact and or a series of fatigue loads that you need to consider. All of those can be considered using the smaller dimension analyzed purely statically, and applying for the larger dimension, that is the reference surface of that plate or the reference curve of the beam. For that, you are applying a pure dynamics problem. You would still get as good results as you would if you were to apply a 3D finite element analysis both in space and time. A spatiotemporal kind of a model that you would have for a 3D model, you might get almost same accuracy by doing just the smaller dimension, analyzing its statics, feeding the results of that into the larger dimensions spatiotemporal problem, and therefore the overall CPU time that is involved in both these problems is still much lower compared to doing everything in 3D. For a beam, it could be of the order of a reduction of 100, and for a plate or shell, it could be of the order of reduction of 10 or so. So in either case, you're essentially bringing in, especially for design kind of problems where iteration is involved, optimization is involved, you will bring a huge savings in the time involved with the analysis. So I think a couple of minutes are there. Let me just go through the engineering technique as a basis for the classification. Very straightforward. You either have a theoretical analysis or you have a experimental analysis. And as I said, as we keep on increasing the confidence levels of these theoretical models, which is both the analytical as well as numerical, you typically tend to postpone or minimize the experimental tests, which involves, of course, the fabrication of specimens, lab level tests, then going to structural component level tests of, let's say, the spar alone, the stringers alone, etc. Then when they are attached to the wing as a component of the aircraft is being tested. So many of those tests would be in the ground before even the first prototype has its first flight. So a lot of things need to be demonstrated, certain certification requirements need to be fulfilled at that level. And then once the entire aircraft is built, still there might be certain flight-based testings that are done as part of the flight testing. Many of these things done on the ground, including the lab level specimen tests, might be destructive evaluations, whereas most of your flight level tests are non-destructive evaluations. But there are certain crashworthiness tests and things like that you might have to do even on a flight in terms of its crash and things like that, depending on the kind of category of aircraft that is involved. But the tendency in all of the aircraft industry, whether it is commercial or military, is moving towards reduction in the experimental investments and an increase in the theoretical investments. And also in terms of experimental, the kind of NDE techniques, more and more advanced techniques that are coming up, and utilizing combinations of those, because certain techniques might give you certain information in the diagnosis, certain others might give you something else in a more higher level of fidelity. So you might want to appropriately combine those in order to make those understandings. So I think we'll try to look at the other 4 classification bases in the next class. Thank you. So anybody has any questions, you can ask me. So we're done with the class.